So for today's seminar, Samriddha was Samriddha of Lahiry, with a postdoc at Harvard in the Statistical department. And before this, he did his PhD from Colorado University. Before that, he was a PhD and started with i.i.d. And today we're talking about quantum states to inference, but he also was in classical things. So he's here till tomorrow morning, and then he's going to i.i.d. So you can also go and hear talk again if you want, and all the talks about classical this evening or tomorrow. So
thanks a lot for the nice introduction and for the invitation. It's an honor to present here. So the title of the talk is quantum statistical inference. So this is based on the joint work with my PhD advisor, Professor Michael Newsom at Cornell. So this will be the basic setup. We won't go into the details about this exact physical experiment, but what we'll have is like a state, which will be a quantum state, and an experimenter passes this state through something called a measurement, which will also be some abstract thing for our talk, and then he or she gets the value omega. And from the value omega, you have to decide what your initial state was. So, I mean, a typical example is you take a qubit or a quantum state, you pass it through some measurement, and you get a classical bit. You repeat this for a number of times, and then you get a large number of bits, and from that you have to guess what the initial qubit was. So the experimenter can choose the measurement m, and then from this conditional bits, he or she infers about the state rho. And the question is, what choice of m results in the best guess for rho? And this is important in the field of quantum information theory. So any question on this?
When you say repeat many times, what does that mean? Some independence there? Or?
Yeah. So you take independent copies of this qubit and repeat it first. Okay, so I will briefly review some classical notions of classical statistics through which the lens of which we analyze these quantum models. So everything will be from scratch as long as the quantum models, as far as the quantum models are described. So statistical model is given by this collection of probability measures, which are indexed by some theta, and then what you get is n i.i.d random variables with the distribution in theta, and you ask what is the best estimator for theta. So you want to quantify what's the notion of best. So what you do is you take a loss function, which is usually taken as the square loss, and then you define something called the risk. So the risk is the expectation of this loss with respect to this probability p theta. So this is kind of a distance between this theta and theta hat. So if it's large, then your estimator is bad. If it's small, then your estimator is good. Okay. And then, so to decide theta hat, so you cannot decide it. So for each theta, you may get different optimal theta hat. So to get some notion of uniformity, what you do is define the maximum, or the average risk. So the maximum risk is you take the risk and you take supremum over all theta, and in the average risk, you take the risk and you take expectation with respect to some other probability measures on the space of theta. And then you can define the best estimator, which in the first case is called the minimax estimator, where you take the supremum of risk and take the estimator which minimizes this maximum risk, and in the second case you take the estimator which minimizes the average risk. So the first one will be called minimax risk, and the second is the base risk. So typically, as your number of sample grows, this goes to zero at a certain rate, which the rate will be called, we will call this rate psi of n, and we'll be mostly dealing with the minimax setup, but in some scenarios, base risk will also rise. So the psi of n is typically 1 over n if this theta is a finite dimensional subspace. So if you can think theta as like a compact subset of RD. If that is the case, then this is 1 over n. And what to get like a finer perspective on this result, you can do is you take psi n and multiply it throughout this inequality, and you want to see if there if a limit exists, and if a limit exists, you call it a minimax constant. So this is called a minimax constant, and if there is an estimator which achieves this minimax constant, then this is the absolutely best estimator in this scenario. So any questions on this?
So suppose the L theta had the expectation it's kind of concentrating for one theta, then the two risks become similar as n becomes larger. Does that happen?
No, I'm sorry.
The base risk,
Yeah.
suppose the integrand is concentrating for large n, supremum is achieved at a particular unique.
So you're saying that these two are
Does it become
similar?
similar?
Yeah.
That's
If this
the-
concentrate value.
So this is kind of standard stuff that they become
Yeah.
similar?
It's kind of so usually base risk is a lower bound to the minimax risk, but if it concentrates on certain quantity, then they are.
Right. Then you can convert that.
Okay, so we need to develop the notion of best in the quantum scenario. So what we are going to talk about are what are quantum models from the basic setup, how they're related to classical models, and what are the quantum equivalents of Gaussian models, because Gaussian models are easy to analyze in the classical setup. What are the equivalents of i.i.d. models, not necessarily Gaussian, and how we can formulate the minimax and base problem to this quantum model. So this will be the main goal. And accordingly, so this will be the outline of the talk. So the first part will develop all these notions, and the second and third part I will describe two results, which I will use the notion from the first part to obtain results in these two scenarios. The second one will be an infinite dimensional setup, and the third one will be a finite dimensional setup. So with this, we start from the basic definitions. So you start with a complex inverse space, which can be a d-dimensional complex inverse space, or you take the space of all functions on R, which are square integrable. So complex valued functions which are square integrable. And on this space, you define self-adjoint operators, rho. They have to be positive and normalized, so the space should be 1. And they're called pure states if they are projection, one projection. So it's like a VV transpose, or in this case psi star. So they're dealing with a complex setup, and it's called mixed state if it's a convex combination of pure states. So again, this lambda j should sum up to 1, so that this space of rho is 1. Okay, so this is states, and now we want to define something called a measurement. For measurement, we again define it through something called an observable. So observable is a self-adjoint operator, and what you do is you take the self-adjoint operator and you do a spectral decomposition. So these pi j's are the projectors and mu j's are the eigenvalues. So we say that this generates a random variable which is discrete and which takes the values in the set of eigenvalues with the probability of taking eigenvalue mu j given by this root trace of rho times pi j. So pj is the probability of excess taking value mu j. And a simple computation shows that if you take this probability, then with that you compute the expectation is just trace of rho excess.
Is probability the positive, non-negative probability?
Yeah, this is always not. So, any questions on this setup?
What is span? What is span here?
Pi j's are the projectors. So it's the projections on some substrate.
What is over there?
What is rho?
Rho is the state. So if I go back a few slides, so I want to define this in a proper setup. So rho is a state and m is a measurement. So I want to define rho mathematically and then define the m also mathematically. For m, we use something called observable, and then we go to more general setup where you use POVMs to define measurements. So rho is the state we define using these things. So this part defines states and this part defines measurements. Any other questions?
So finally about problem.
Yeah. So let's look at some concrete examples. So here are qubits, which are quantum states in situ. So these should be self-adjoint operators. So in situ, these are just matrices. So you parameterize them through these three numbers, Rx, Ry, and Rz. And if you define three matrices, sigma X, sigma Y, and sigma Z, then you can write this rho R, the qubit, in terms of this quantity. So these are linear combinations of these matrices, and Rx, Ry, and Rz are the coefficients. Okay, so sigma X, sigma Y, and sigma Z are observable because these are all again self-adjoint operators. And what we can do is we can do a spectral decomposition of sigma X, like 1 times pi plus 1 and minus 1 times pi minus 1, where pi plus 1 is this matrix and pi minus 1 is this matrix. So I'm just doing a simple spectral decomposition. Now, we know that from the previous slide that this will generate a discrete random variable. So sigma X here will generate a discrete random variable with x sigma X. So x sigma X, if x sigma X is the discrete random variable, so it takes the value plus 1 with probability trace of rho r times pi plus 1. It takes minus 1 with the probability rho r times pi minus 1. And if you compute this trace, so this is this matrix multiplied by this matrix, and you take trace, we get half times 1 plus minus Rx. And the expectation is Rx, and again you can see you can show that if you take trace of rho r times sigma X, then you will get Rx. So any questions on this one? So we have defined what quantum states are, we have defined what observables are, and this is a concrete example of this one, of the setup, and then we can compute the probabilities and the expectations. Any questions? Okay, then moving on. To define measurement in a more general setup, we need to define something called a POVM. So you are given a measurable space, some omega, some world sets, and we define POVM as an operator value measure. So it eats one world set and outputs an operator. So LH is the space of all bounded operators, and this operator should satisfy three quantities. This MB should be greater than or equal to 0. So if BIs are mutually disjoint, then M of union BI should be sum of n BIs, and there should be normalization. M of the entire thing is 1 or identity. So these MBs are all operators. So if you look at it carefully, you will see that these are like the operator valued analogs of the axioms of classical probability. Should be greater than 0, there should be only additive, and then the total probability should be 1.
So how are they different from probabilities?
So these are all operators.
That's okay.
Okay. Now if you take a POVM and you have a state rho, this P rho of B is the probability of the outcome. This is given by this trace rule, trace of rho times NB. So this is same as the thing that we saw before. So it's rho times ij. This is a more general
I can just trouble you a little bit. Because the way I think of operators is maybe it's a generalization of matrices and all that. So what does MB being non-negative mean then?
Is the usual non-negative matrices. Like the positive definite.
Okay, so inequality in the matrix set. Okay.
Sorry?
So inequality is in that for the matrices.
Yeah. So it's
Alright. Okay, these are all well-defined notions.
Yeah. Okay. So you want to have a setup where you can also generate continuous random variables. So you can take an observable. So this is again a self-adjoint operator in a general input space. You have the spectral decomposition, which is a generalization of the finite spectral decomposition we have for matrices. And the sigma s is the spectrum. And yes, this M this M out here. Okay. And the expectation is trace of S times rho. If you just multiply.
So where what is it? So S is sum of. So S is like a.
S is the observable, so you self-adjoint.
Okay.
So I do a spectral decomposition.
But is it spectral decomposition with respect to the M measure? With the map M.
With respect to some measure M. So this is like the spectral measure. The spectral measure is operator value measure. And this is a POVM. So all POVMs are not of this form.
Yeah.
But for this one, this is a POVM.
Okay.
And then if you generate, if the random variable is generated according to this law, then you can compute the expectation of x in the space of S rho. You can just multiply rho and take the interchange the trace and integral, and you see that this is trace of S.
No, but there's something here about M, right? So M was fixed, so that was a measurement, and then so which it's a measurable function.
Yes.
And so this integral. So now you're like, so it also defines a measure. So what is dx? So where is x? X is sitting in
M is an operator, so M is not a measure. So
M is an operator. So okay.
Yeah. So in the general case.
Oh, okay. I see. So x s m. Okay. So the integral is just Lebesgue integral.
Yeah. So this is a spectral decomposition for finite dimensional. I mean, it's a compact operator or something like that. So you have mu j times pi j, and then that is like so the pi j's are operators. So if you want to generalize this to a continuous setup, what you have is this.
So all I see is that this okay. So maybe what I'm getting into is what you want to write is x times m of x times mu of dx, where mu is for times sigma of dx, or where sigma is the measure coming from s. So what the observable s is defines a measure on the x's, and then for each x you have the term which is x times m of x. So x is the element of omega, right?
Yeah.
And m of x is an operator.
So
and then you're taking integrating operators with respect to some normal measure.
Yeah.
Like a usual measure.
Yeah.
So it's like
the easiest way to think is you multiply it by some vector v on
you can. So it's like x times m of x times mu of dx, so then sigma of dx.
Yeah.
That.
So you have m of dx.
No. So we instead of m of dx, we write x times m of x. X is the element of omega.
You can do it, but
I didn't make sure that's what it is. So x times m of x.
Okay, so if A has some kind of a density, then you will do that. Otherwise, you can. So it's
no, but if m has but m was not the measure. The measure is so
M is not the measure. M is so okay.
So what is the measure with respect to which you are integrating?
F is an operator.
Yes.
So this is called a spectral decomposition. So the interpretation of this is like if you take.
No, so this m is not the same as the POVM then, or what? So the POVM also.
Okay, first concentrate on this m. So this m is a spectral measure of this s.
Okay.
And this is also POVM because it satisfies all the quantity.
Okay, so
this is an example of POVM.
Okay. So
and this is just
for corresponding to s, you have a So for corresponding to s, so m is a function of s, no?
M is a function of s.
Yes. Okay, and
now this is a measure. So
now this
is the measure and
because of the
yeah. So
because
this
of
is
one.
the notation which means like
Okay.
when the
Okay. So yes, so the M is not fixed. M is what is coming from S.
yeah.
Yeah.
So you get to choose M
Yeah.
or you get to choose S.
Yeah, which is M.
S or M. So how is this related to classical probability? So if the all thing commutes, then you are in a classical setup. How to visualize this? Suppose we have a probability distribution with support A1 to AD. You take the probabilities, you embed it in a diagonal matrix. Now all these are positive, so the entire matrix is positive. And the trace is 1 because the sum of probability is 1. So this is a quantum state. So if everything commutes, you can actually write the probabilities in a like this. Now I want to define something called i.i.d models. So how to define i.i.d? So i.i.d in classical setup comes from the product measure. So we start with a simple probability distribution on E1 and A2. You can think it as a Barton random variable with 0 and 1, something like that. And then you compute the product measure. So this is the product measure. And interestingly, if you do this embedding and take the tensor product, then the tensor product is exactly same as this product measure. So you take this, do the tensor product, and look at the elements in the diagonal, and this is exactly same as this. So the tensor product is same as the product measure when everything commutes. What we do is like we define i.i.d or product in the non-commutative setup as well through this tensor product. So these are just tensor product of operators. Any questions on this?
Very basic question. The first part represents the probability distribution for each of the for each of the support variables.
Yes.
And what is the second thing? This matrix.
This one?
Yeah.
Or this one?
No, the second.
This one. Yeah. So okay. So this p theta, this tensor 2, that actually denotes product measure when these are probabilities. So this you take x1, which is distributed as x, this one, and you take x2, which is distributed as same thing x2, and you want to see what the joint distribution of x1 and x2 are. So this is the joint distribution. To compute joint distribution, this is the joint distribution.
Okay. So probability that x1 is equal to a1 and x2 is equal to a2. Okay.
x1 is equal to a1, x1 equal to a2, x2 equal to a, sorry, x1 equal to a1, x2 equal to a1, this x1 equal to a1, x2 equal to a2, and so on.
Okay.
So this is the product measure. And then, yeah, you can do the model. So in the non-commutative setup as well, you take your original quantum states and you do tensor product, and then what you get is i.i.d model. Okay. So this is the summary. States are analogs of classical probability distributions. Observables are analogs of classical random variables. Tensor product of states are analogs of product measures. And measurements are quantum to classical randomization, because if you fix a measurement, what you get is a classical random variable which is distributed according to P rho, which depends on the points. So this is the summary. Any questions? Okay. So instead of a classical model, so a classical model is a collection of probability measures. What I'm doing, what defining is a quantum statistical model, which is a collection of quantum states. So I'm replacing the probability measures by quantum states. And then using a measurement A model theta, we generate a random variable, which is defined by which has distribution according to this law. So this is basically this quantity. And then I can define my risk, because I have this loss function, and you can if you integrate the loss function, you get a risk. So if you fix M, then your measure is fixed, and you can integrate it to get a risk. Okay. So now I can define the minimax and base problem as well. So I can define the supremum of the risk or the average of the risk, and instead of taking infimum over all estimators, I am taking infimum over all qubits. This is the same thing as just like. So you take the supremum on the average, but you take here you take infimum over all theta hats, but here there we are taking infimum over all the periods. Okay. Okay. Now I want to define something called a Gaussian state. It's a little bit more complicated. So these will be analogs of normal distribution or Gaussian distributions. So there, the observables are operators because we are now in a high-dimensional space. So this Q is the multiplication operator and T is the derivative operator. So these are called position and momentum operators in physics. And you define it over some dense subspace of L2R. You take the linear combination of these operators, and you can define something called a quantum type function. So you exponentiate this operator, and multiply it by rho, take place, and you call it quantum type function. And if that matches the characteristic function of a Gaussian distribution, so this is the characteristic function of a multivariate Gaussian distribution, we will call it a quantum state, quantum Gaussian state. And in analogy notation, we'll say that it has a mean mu and the variance sigma. So it's a little bit abstract, but it can be defined. So these are two examples. So if this sigma is half time identity, we'll call that shifted pure state. If it's sigma squared beta time identity, we'll call a shifted thermal state because of this parameter beta, which is often related to something called a temperature. And if beta is infinity, then you get back this one. So you just plug in, we take away infinity here, and then you get back this one. So why are they called shifted? Because the Gaussian distribution with mean mu is called a shifted Gaussian distribution. If we think as the standard normal as normal 0, 1, so normal mu 1 is like a shifted normal. So here in analogy to that, we defined shifted pure state and shifted thermal state. Okay, so these will appear in the limit, but we will not go very deep into this how to construct that. But these are all quantum states in a infinite dimensional setup. Any questions on this?
So in terms of, let's say, so what does it look like if I want to write it in terms of the position basis or momentum basis?
So it's a little bit complicated to write that. So basically,
so even at the physics level, let's say we are around delta functions and so on, so it's still not. Oh, because there is this. Okay.
I think for the shifted one, it's a bit difficult to write. But for this one, it's easier to write because what you do is you take the harmonic basis, and then
in harmonic basis on the positions or any one.
Yeah, in any of them, and then so the basis is like you use the creation operator to define the basis, right? So 0 plus 1, those kind of thing. So you get the basis.
But it's country. So like there's no discrete spectrum anymore. So
No, I'm not saying a spectrum. I'm saying this defined on a Hilbert space, right?
okay.
So in the L2R, you can use the Hermite basis to define.
Okay.
Hermite is the basis. So this is like 0, K0, K1, K something like that, right? So this
is some countable
basis. And then in that basis, so you take a linear combination and then you multiply with. So then if you do not, okay, so this shifted thing looks like this. You want to get see how it looks like. So suppose mu is equal
It's
to
a
1.
pure state. It should just be a function.
Yeah, it's a function, but for the thermal state, it's something like this.
Yeah, but the thermal state will be actual mixed state. But for the if it's called a pure state, it should probably just be a function from like in L to R. Okay.
Something like this.
Oh, and then you're taking the limit as beta goes to
infinity, then you get the So you only get the first one, and then you multiply it with some unitaries to get this mu. Or to get this.
So, and that 0, 0 is actually the Hermite 0.
Hermite 0.
This way of kind of taking objects from probability theory and coming up with the analogies in the quantum world, does this go very far? Can you have a central level theorem? Can you have multi-layer?
Yeah. We have it.
So, I see.
But the central limit theorem is very difficult to understand. I will describe something which is similar, but which is easier to understand. But the central limit theorem actually requires knowledge of sister algebra and stuff like that. So that part is a bit difficult. But so the reason for defining Gaussian states is like we want to approximate these qubits by the Gaussian states. And if you have a good estimator in the Gaussian model, then you have a good estimator in the original qubit model. So that's the main that's the fundamental paradigm. So Gaussian models are easier to analyze. Okay, so here is a very nice example. So you have a quantum Gaussian state, you have a prior distribution, and you ask what is the basis for estimating mu. So you have actually a closed form expression. So this goes back to Olevo in 1973, where he computed that this is the function of sigma squared and sigma naught squared. And I have written this in red because you can compare it to the classical setup. So this is a classical base risk. So you see that there is, if you remove the plus ones, so you get back this quantity. So this one is higher than the classical quantity. And the risk is higher because of the non-commutativity of the scenario. Basically, you cannot estimate position and momentum simultaneously. You have some kind of Heisenberg uncertainty, and because of that, the risk is higher. If time permits, I will describe the POVM that can be used to get this risk. So basically, there exists a POVM which generates this classical random variable, and you multiply it by some constant to get the optimum and a very optimum measurement that gives the base risk. So this will be used a lot. So this expression, or rather this result, that we can actually get an exact value of the base risk in the Gaussian setup. We cannot get an exact value in the qubit setups. Okay. Any questions so far?
What is non-commutativity over here? What is being
Right, good question. This Q and V do not commute. Position and momentum will not commute. Okay, so this will be the scheme. So I use some theta to parameterize the state. I take n-fold tensor product, and I want to guess what the theta was. So I expand theta in a local region, so theta naught plus h power minus half h, and I want to get a measurement which will give me a random variable, and then from that I want to guess what h in hat is. Instead, what I will do, I will approximate this thing by something called phi of h. This will be a Gaussian thing. There I can compute the m. So yeah, you can actually get the m in the Gaussian setup. So there we can use some m to generate a random variable and then generate an estimate of h as h hat. And it says that if h hat is an optimal estimator of h, then h hat is an optimal estimator of h in the original setup. So if these two models are well approximated in the centimeter sense or any other sense, then these two POVMs are optimal limit. So now we want to define the approximation scheme. So for that we need a notion called asymptotic equivalence of experiments. So suppose you have two collection of measures. So first one is P1 theta, theta belongs to capital theta, and the second one is E2 theta, theta belongs to capital theta. And what you do is you will use a Markov kernel to which you can take as conditional probability distribution for all practical purposes to translate this measure to the space where P2 theta lives, and then you can compute the total variation norm. You take the supremum over all theta and then infimum over all Markov kernels. And then we get what's called a deficiency. But again, we will not go into detail how to construct kernels, so you do not need to worry too much about that. So it just means that I am translating one experiment to the other, and delta distance is just symmetrization.
So is this a well-known notion, deficiency?
Yes.
It's already well-known. Okay.
This is called deficiency, and this distance is called the delta distance. Okay. So it says that suppose I have a decision rule or I have an estimator in the first experiment, say that's a delta 1, and suppose this deficiency is less than epsilon, then the maximum risk in the first experiment cannot be more than the maximum risk in the second experiment plus epsilon. Okay, so suppose I compute the risk, I know how to compute the risk in the second experiment, P2 theta, and I want to know what the maximum risk in the first experiment will be. So this cannot be more than this. And if the delta distance goes to 0, then we call that asymptotically equivalent. The practical events show, actually, a stronger form of center limit theorem is to show that the binomial distribution can be well approximated by the Gaussian distribution in this sense. So if you apply CLT, you cannot do the same thing, because if you take the total variation norm, one is supported on discrete space and the other is supported on the continuous space. So the total variation norm does not go to 0 for the binomial and the Gaussian. So, but if you use the Markov kernel, then there's 0. Then this is well approximated. So how to look at this? So basically, how to look at this Markov kernel? So these are, say, the binomial probabilities. Okay, something like that. You cannot approximate this by Gaussian distribution. So what you do is you add some kind of bars on that. So this is the effect of the kernel, roughly speaking. And then you can approximate it by Gaussian density, something like this. So the Markov kernel is just adding some noise so that you can approximate. So this is a classical notion. For quantum setup, we define something called a quantum channel. Again, these are just preserving completely positive maps, and I don't want to go into details. So this actually is an analog of the Markov kernel. And the L1 distance between the two states is defined by the square root operation. And this is an analog of the PV distance. So you replace the probability measures by this the quantum states and the Markov kernel by these quantum channels. And if you do that, you get a quantum definition. So if you look at the definition, I have these probability measures, I have this Markov kernel, PV norm. Here I have these quantum states, quantum channel, and L1 norm. So these are just operator value thing, analogs of the original thing. And here is one small lemma. It says if loss grows at most like Cn, and you can show that there exist a channel such that this quantity holds, then the minimax risk in the first experiment can be more than minimax risk in the second experiment, plus some small word term.
So here it's very important that the T or K should not depend upon the parameter.
Exactly.
But the notion seems to make sense even the other way around. It is like it's not trivially become zero. So if I had only one theta.
Sorry?
So if I had only one theta.
Yes.
And it does. But yes, so if
No, it will become because they're doing a supreme argument.
No, so I'm saying, so suppose there was only one. No, I'm saying that is it true that for any two probability distributions, I can always find a kernel which maps it to the other with while the total variation by meaning the total variation is still zero? Probably yes. Or not, we don't know. So I have two probabilities. No, I can't. No, you can. Okay, that's
Of course.
Yeah, you can't.
So let's see the slides before this.
Yeah.
So P1 and P2 are now not probability measures, they're collections of probability measures.
Yeah, P1's okay, I realize that. So P1 theta and theta belongs to theta is a collection of probability measures, P2
Right.
theta is
And then you're saying somehow they are close.
yes.
It's
So
like-
they are called experiments. If you index the probability measures by some theta, they are together, they are called experiments. And these two experiments are close. If you can show that two experiments are close, then you can compare the risks. And here what I'm doing is I'm saying that the two quantum experiments are close. I'm just replacing the quantum, the probability measures by the quantum states. Okay. I think that's all for the preparation. It's still a bit heavy, but I'm going to, I'll come back if necessary. Yeah. So this is the first result.
So basically the point is that a classical operation is really like what people can do in a classical algorithm is basically a Markov kernel. The quantum algorithm is a quantum kernel.
Yeah,
That's
exactly. You just translate all the notions from classical quantum setup and then. So what we'll do is like we take binomial and we approximate it by Gaussian, and in Gaussian you can do all the good operations and see that this is the kind of the best operation, and then we can say together this experimental notion that this is also the best in the binomial setup. Here what we'll do is take a class of qubits, we'll approximate it by some quantum Gaussian, and because they're kind of close and we know how to handle quantum Gaussian, we'll know how to handle the qubit system. That's the main setup. Okay. Okay, so I will go through. Okay, so this is the first result. It's a non-parametric extension problem. It says that suppose you have a Gaussian sequence model. So this is a stochastic differential equation. You do not need to worry about that. So if you take Fourier transforms, you get this Gaussian sequence model, which is like yj is a theta j plus 1 over root is like this, and this is like infinite. So j is equal to 1, 2, 3 up to infinity. So this is the model, and you restrict your theta j to some space, which we call the Sobolev side. So this alpha j is a j bar 2 beta or j bar minus 1 over 2 beta if its j is even or odd. And then you have a Pinsker theorem, which says that you can do a minimax estimation. So you can get the rates, which are xi n, since n part 2 beta by 2 beta plus 1. But also, if you multiply by xi n, you can also get the constant. So this is the first slide. We multiply xi n, you get the constant. So if this happens, then a good set. This is the best thing that you can hope for. Here, is again a 1980 result. It says that if you estimate in this model, then if you multiply it by this rate, you can also get the constant. The first result is the quantum version of this result. So we will do something called the quantum Gaussian sequence model. We establish result there, and then use symptotic equivalence to transfer risk. So risk transfer will be something like this one. So this is kind of what we call a risk transfer. So maximum risk there is cannot be more than this one. Okay. I think I have enough time to cover, so I'll skip a bit. So what we do is like you take your states. So these are radical operators. Okay, and you parameterize this locally, in some sense. So it's like, so you don't have to worry about this one. This is kind of the for the normalization. So you perturb psi naught with some u, which is a vector, and then you take the tensor product of this model. And I want to approximate it by a Gaussian thing. So what I do, I take a u, I expand it in a Hermite basis, I take the coefficient, I create a Gaussian sequence model with this one. This is a quantum Gaussian sequence model. So the basic idea is to replace product measured by tensor products. So here, where is this? Somebody may skip this slide. Okay. Okay. So first, I should go back and define what quantum Gaussian sequence model is. So I want to replace the product measured by the tensor product. So consider a tensor product of quantum Gaussians. I restrict it to some super side, and then I get the Pinsker type result. So this is the first theorem. So we get the rate as well as the constant. So if you look at this is the classical Pinsker result, you get rate and constant. And these are all product measure because these are across the J they are independent. So what I do is I replace the product measure by tensor product, and I want to get the rate as well as constants in the Gaussian model. What I do is we get the same thing. We replace the product measure by tensor product, and then I get the rate as well as constants. Okay. And then I want to do the same thing for pure state model. So again, coming back to that model. So I do a local expansion, I take a tensor product, and it can be shown that this model is asymptotically equivalent in the Lacan sense to this Gaussian sequence model. And I know how to compute minimax risk in this model, and then I can compute minimax risk in this model. So minimax risk in this model is just this result. And by the virtue of risk transfer, I can compute minimax risk in this model. Okay, so here is the result. So you take some notion of smoothness, so this again this so some Hermite class, and because of this, we know how to compute exact risk in the Gaussian setup. We know that these two models are closed, and we can do the same thing in the i.i.d. model as well. So I can discuss this offline and information if someone is interested, but we don't need to go into detail. But the paradigm is always the same. We approximate it by Gaussian model, get the rest estimator there, and use this transfer to get the same in the i.i.d. model.
So you're getting better convergence rates for larger betas. Is that right?
Yeah, the smoother they are, the
Smoother they are. I see.
so this beta represents kind of smoothness. So
Let's see.
so this Sobolev ellipsoid, if you look at this at the functional level, so this betas for the coefficient translates to the smoothness of the original function. So higher beta means the function is smooth. So this theta is a Fourier transform of this one.
Higher beta means theta decaying fast.
Faster, so that means every smoother. Okay. Okay, so that's the result. Okay. Now I want to describe something which is a finite dimensional statistics or the parametric model. So we look at an old result which says that okay, suppose you have some regularity conditions which are called DQM or differential equality mean. It means that you have a collection of measures which have a density p theta, which satisfies this quantity, which is kind of a regularity condition. Then you can approximate this experiment by a Gaussian experiment. You take theta naught, perturb it in a root n, so n power minus half root, and then you take n-fold product measure, then you can approximate it by this normal experiment where I know the Fisher information. So what is a good example? So you take a multinomial distribution. So this is like supported on the alphabets. These are the probabilities. You perturb this mu i's like this, and you get a multivariate normal distribution. So if you perturb multivariate multinomial distribution, you get multivariate normal distribution with the same covariance matrix. Okay, so I want to establish this in a quantum setup. So what I want to do is I want to add perturbation to my quantum states. So for that, what I do is like I take a d-dimensional density matrix. So this is a d cross d complex matrix with rho greater than 0 and rho equal to 1. So this is the quantum state. What I want to do is I do perturbations because it's a matrix. So you want to perturb it both the diagonal elements and the off-diagonal elements. Or you can look at like this, that if you want to perturb both the eigenvalues and you want to perturb some kind of rotation. So what you do is you take a quantum state, which is a diagonal state of mu1 to mu d. So this is a diagonal matrix.
So classical.
Yeah, this is so. If you look at it as a vector, this is a classical vector, classical multinomial distribution.
But it's also a classical state, which
It's
is
a classical state. But when I perturb it, it will not be a yeah. So I do. So first of all, I perturb the eigenvalues like this, and then I do a rotation perturbation. I want
now it might not be a trace one.
it will be a trace one.
No, but that perturbation is adding something. Oh, u is trace, u is 0.
Yeah.
U is some 0.
Yeah. Some of you should be 0. I found it right here. So this is the eigenvalue perturbation, and this is the rotation perturbation. So commutaries, you do a tensor product, and then this is the limiting Gaussian model. So it has a multivariate classical part, and it has a quantum part, which is a collection of mixed states. These are all thermal states that I defined by defining the quantum state. So the Gaussian. So this. So these are these shifted thermal states, and they appear in the limit.
But it's still tensorized. So can we go back to the
Yes.
So
So for all the off-diagonal elements, you get one on quantum quotient. So you can think it like that.
All the elements, you get one quantum.
And for all the eigenvalue perturbation, you get a classical part. For all the but that's not independent. But for all the off-diagonal perturbation, you get independent quantum quotient.
So this phi theta is not a quantum state or anything. It's just like it's
No,
something.
phi theta is a quantum state.
It's quantum state. But
So
then
I want to approximate this one by
which space is it living in? So this oh this is again that same normal notion, the whatever the notion of normality for so it's okay. So this is living in the infinite. So
yeah, this is the.
so
you can actually
now you have like d squared systems.
Exactly.
Each one of which is so it's like L2R to the power d squared.
Exactly.
That's correct.
Exactly.
The original thing was living in d dimensions. The original state was living in d dimensions.
Yes.
No, actually not d dimensions, d to the n. Oh, okay, but this is the thing. So the original state was living in like cd to the n.
Yes.
C to the n, and now this limiting thing is living in I2R to the t squared. But okay, so and then they're asymptotically equivalent.
They're asymptotically equivalent. So that was the result that was shown in 2000. But what you have shown is like if it's a prime card, so what you do is start with a diagonal matrix with only R eigenvalues positive. You do a eigenvalue perturbation, you do a rotation perturbation, and you want to check what your limiting Gaussian model is. You get a classical part. You get a quantum part which is mixed states for 1 to R, and then you get a quantum part of pure states as well. You can show that these two ones are classical asymptotic equivalent.
So how does this asymptotic equivalence change under like just basis change? So if I just take rho, the rho theta naught, and apply some arbitrary unitary and u dagger, like put it in between u dagger. So it's again, if the eigenvalues don't change, it's now an actual quantum state, and it's not in the computational base anymore. And again, this rho theta star n can be defined in the same way.
Yes.
Maybe not.
But it depends on if you know the emitter is unknown. If the emitter is unknown, then it is the same thing.
The same thing, because but if they are not known, then how will those unitaries show up in? How will they modify this phi theta r?
You can multiply. You can actually again reparameterize those unitaries, and then the parameterization will change, and then
So this will be the same. In terms of distributions, at least they will be the same, because it's generating the same. So u is being chosen from some. So where is u being chosen from?
U.
Yeah, so the eigenvalue perturbation is not a random vector. It is that's a hidden. That's the thing you want to estimate.
Which one? U.
So small u and capital.
Yeah, how small u and the zetas are the parameter, because this mu and mu's are fixed. So why is this low rank thing interesting? Because suppose we do not have any unitaries. So this side is a 0. So what's the limit? So this whole thing vanishes, and you just have a classical part. So you're basically perturbing this classical thing, and you're getting a multivariate normal. So you're perturbing multinomial, and you're getting a multivariate normal. So that's a classical result. So
that should be there, right? Because
that should always be there. Okay. The non-degenerate case is trivially included, because if R equal to D, then this part vanishes. So you have this and this, which is exactly this result. And for R equal to 1, you only have pure state, which is equal to. Okay. So R equal to 1, this two vanishes, and you have only this. Which is interesting, because in the infinite dimensional setup as well.
So R equal to 1 means you're in a pure state.
Pure state.
Quantum. You start with a quantum pure state and you remain in the
pure state. So you start with the pure state, you end with the pure state, but this is like up to finite d. But if you look at this result, You start with the pure state and you end up with the pure state with infinite tensor product. So this is like the next result is like a finite dimensional version of this result. But both are obtained like with the separate, completely different arguments, but we still have this nice thing that pure state always results in pure states. Okay. And then again, because this local asymptotic equivalence holds, what you can do is you can compute the exact minimax list for these qubits or d-dimensional quantum states, and these are functions of this mu, the values mu. So this minimax list actually decays like 1 over n. So what you do is multiply by n, and you want to evaluate this constant, you can get the constant. Again, the preliminary, there are some preliminary estimators, and we use the local equivalence for the upper bound. The lower bound uses base result. The original whole level result is used for this one. And there is another problem.
So this asymptotic equivalence is not equivalence of measurements or even the classical figure. It's like whatever you can do in one, you can do in the other, but the algorithms might be very different, or the estimator might be very different.
Technically, you can actually lift one estimator to the other, but that's computationally very hard.
But the risks will be converging.
This will always converge.
That's
okay, so there is another result. So you want to estimate this linear functional. So you multiply this your state with some matrix A and you take the trace. And again, you have this kind of result where you get the exact risk, you get the rate, which is say for half. So this square, so you get the 1 over n rate and you get the.
So this was the expectation of a measure. So A I should think of as the POVM or.
Which one?
So A is like the POVM or something.
Yeah, the spectral measure of A is the POVM. Spectral decomposition. Again, so we get an exact result. So this is a linear functional, but you can estimate other functions as well. You can try to estimate von Neumann entropy, which is not a linear functional, but that's kind of open. So here is an open question we could not solve. Is we know that for rank 1 pure states in the infinite dimensional case, you only get pure states. For rank R infinite dimensional setup, you actually get this result, but we do not know when you have rank R, but the setup is infinite dimensional. That we do not know. So what if d equal to infinity? We do not know. So that's the conjecture. If d equal to infinity, just d equal to infinity.
And von Neumann entropy also.
No, von Neumann entropy is completely different. I'm just saying that that's a linear. That's also a function.
Yeah, but it's non-linear things. Any of this is.
It doesn't cover non-linear things. Yeah. So this is the brief summary. The optimality equations in quantum information theory can be formulated in the language of mathematical statistics. So all the minimax and basis result actually continue to hold in the quantum setup. Quantum setup systems are non-commutative, and to analyze them, we need new kind of tools like this, analyzing these POVMs and stuff like that. The risks are usually higher because things cannot be simultaneously measured, like the position and momentum. In a classical setup, Gaussian distributions are easier to analyze, and you can compute exact asymptotic minimax result there. Likewise, in the quantum setup, quantum Gaussian states are easy to analyze, and you can compute exact minimax results there, which some of the theorems have shown. And quantum local asymptotic equivalence can be used to transfer risk between i.i.d. modes and Gaussian models. Just like in a classical setup, you can transfer risk. So these are the.
So one more question we so this quantum Gaussian, like, is an analog of the heat equation or blocks over there? inequality or Poincare inequality.
You mean if there is an analog of
So basically, like in the Gaussian case, I can relate to Gaussians via I can think of it as a there's some dynamical thing that the
Yes.
equation deforms one Gaussian to another. Is there some natural analog?
I think that's a bit harder to do because like here, if you want to define Brownian motion in the quantum Gaussian, that's way harder because first of all you have to define the field equation, and so this will be a collection of Hilbert spaces. That's
changing.
involves. So there is a very good book by Lahiry on quantum stochastic process, which has all this kind of thing. But yes, those are like very characterized, yeah, and then of course you have quantum stochastic differential equation, and you have most of the classical stuff. You have quantum analogs.
But those are sometimes useful, right, for inequalities and all. Like in the classical case, the heat equation
Yes,
sometimes be useful to relate Gaussians and so hypercontractivity or
Yes.
like even when you're not dealing with the stochastic differential equation at all.
Yes.
So it is like a very
yeah.
comparison kind of question. So but those things probably are here also, or not yet developed, or
I'm
not
not
yet
sure
used.
whether if that's explored yet, but probably there is some. I think you may find some results on loss of in this domain, but I'm not sure if whether they are explored yet because this result is high click-up kind of thing. This is like a 70s kind of result in the classical setup, but this result is putting like the full rank case is done in 2010 or something like that, and this is like 2024. So yeah, many Gaussian, many quantum analogs are yet to be developed. But of course, you can always
Parts
find.
of this book is probably from long ago.
Parts of the book is from long ago, but like the statistical. I mean, quantum probability is well developed, but quantum statistics, there are a lot of.
The Stein's method and the
Yes.
one there is.
No, there is not. So there is some kind of variation in the quantum setup as well, but Stein's method is not there.
Yeah, basically like this again the same problem. The defining operator would be some weird.
Yes, I think if you start with Stein's, so there is a notion of Stein's method in free probability. I'm not sure whether you will be able to remodify it in the quantum setup, but I mean, it should. I mean,
but it's characterizing operator kind of thing. Like in the classical case, it's just integration by parts. But here,
I mean, I actually have no idea, but there is one interesting observation, which is this. If you look at this characteristic operator, the first one is derivative and the second one is x times fx. So Q and P are exactly kind of thing. So I would guess that there is some kind of characterizing equation if you start with the Gaussian quantum Gaussian. But yeah, I don't. So probably Stein's method can be. That's a very good question.
The analog of the probability measure in this quantum setup is both the probability and an operator. Like is that?
That's again a very good question. So it's actually operator, but you can actually define systems where you have the classical as well as the. You can define a joint system where you have a classical part and a quantum part. So you can think if there are two parts. First part is commutative and second part is non-commutative. Something like that. Okay, so these are summary and okay, so these are some stuff I'm thinking about. So if we are in a high dimensional setup, how to go about with this estimation problem, and then this estimation of one-ordered entropy, which is a quantum analog of general entropy. And there's also quantum state learning, which I'm working on with Sophie Shang from New Jersey Institute of Technology. So it's basically you have this for each quantum state, you have 1 and 0, and you want to detect which quantum state is giving you one and which point of state is zero. So this is like more in the flavor of classical learning theory. The Hartnett, Chapman, CB bounds and stuff like that, but well, this again is not very lot. So I think that's all. And these are the two reference, the papers. And with that,
So we can end the stream, and after that, if there are any more questions.